Hello students, welcome back. Here comes another application of the Chinese remainder theorem, and that's chapter 6, Polynomial Congruence. In section 2, we studied linear congruence and systems of linear congruences in section 3. So quadratic or higher polynomial congruence is in order naturally, and that's what we're going to study in section 6. Here's a motivating example. 2x cubed plus 7x minus 4 is congruent to 0, mod 5, and then mod 25, and finally mod 200. Which is easiest? Of course, the first one is the simplest, and that's where we're going to start. How to handle this problem? Factorization of those kind of things will not work here. You can clearly see that. One way to handle it is to try all possible entries. X is 0, 1, 2, 3, or 4. There are only 5 numbers to try, so it's an easy computation even for humans. So let f of x be the polynomial part on the left-hand side, and then try all possible x values, 0 to 4. You can easily see that f of 1 is congruent to 0, otherwise all non-zero, so there goes our solution. It's an easy computation even for humans. Now let's go to the next problem, mod 25. One way is to do the same. F of x is the left-hand side and try all 25 numbers, 0 to 24. And then you'll see f of 16 is congruent to 0, modulo 25. Now this is not completely out of hand for humans if you have sufficient time. Still, it's a bit too stupid. For computers, it's no big deal. And in this table, k is running from 0 to 24, and then the second coordinate is f of k mod 25, so the remainder of f of k when divided by 25. And that's 0 when k is 16, you can see that. Okay, too much for humans, but easy for computers. Still, I'd like to find a little bit more efficient way. A little bit more clever way. Why? What if this had been 5-digit number and this had been 25-digit number? Even for computers, it's going to be hard. If you have 200-digit numbers, good luck, even for computers. So how do you reduce this problem? Let's begin with this reduction. F of x is congruent to 0, mod 25. Then f of x is congruent to 0, mod 5. The reason? 5 divides 25. See? F of x is congruent to 0 means 25 divides f of x. In other words, f of x is a multiple of 25. It would have been better with this. 25 times a certain integer, q for quotient. Then 5 divides 25, so f of x is 5 times some integer k. This integer k is actually 5q, but let's just leave it at k. Consequently, f of x is a multiple of 5, so f of x is 0, congruent to 0, mod 5. So we have this direction. The other direction does not hold, of course, in general, but that's a step up because among 25 numbers, from 0 to 25, only the numbers that satisfy this here, which we considered in part A, will be relevant. Those congruent to 1 modulo 5. There are not that many. 1, 6, 11, 16, and 21. Only those. And you can check easily that this is congruent to 0, the others are not. And as for that computation with purely paper and pencil, well, go ahead and try. It's not too bad, but I think it's a waste of time. After all, what we want is a little bit more efficient way. So let's work out the whole numbers that are congruent to 1 modulo 5. I can express those as 1 plus 5t. And then that's going to be your x value, 1 plus 5t, because 2 plus 5t, 3 plus 5t, those kind of things are all out of consideration thanks to part A. And then we can plug in 1 plus 5t in plus of x and expand using the binomial theorem. Now, remember the binomial theorem? You can expand it like that, but it turns out you don't have to expand them all because we have 5 here, because we are doing mod 5 from the previous problem, and we are doing mod 25 now. So 5 squared is 25, or anything higher as 25 as a factor. So quadratic or higher will be all 0. They're not going to play any role. Even if this is 30th power, you don't really have to expand all 30th power using the binomial theorem. You only need the constant term and then the linear term. So take the power, multiply to this linear coefficient, and that's it. All these will disappear anyway. So binomial, don't panic, it's not hard. Just up to the linear term, so it's an easy computation. And then some simplification, and that's what we have. 5 times 1 plus 3t is congruent to 0 mod 25. And then what do we have? Dividing by 5, we get this simplification. Does it make sense to you? 5, and then here 25. So divide each by 5 so that we get 1 plus 3t is congruent to 0 mod 5. Once you get there, finding t value, that's easy because 5 is not a big number, so you can try all possible entries. Or if this had been much bigger number, then, well, you'll have to do it hard way. Flip 1 to the other side, get -1, and then flip 3 to the other side by multiplying the multiplicative inverse. You'll have to find the multiplicative inverse through the Euclidean algorithm for Bezout's linear combination expression of the GCD. That's going to take a lot of effort, but at least that's something you can do, even for large numbers. And by the way, are you comfortable with this? Dividing by 5 and getting to this. If you're comfortable, okay, go ahead. If you're not comfortable, well, here's a proof actually. 5 times 1 plus 3t is congruent to 0 mod 25 means this thing here is a multiple of 25. So 25 times some unit of q for quotient. And then everything is crystal clear now. Divide both sides by 5 and then you get 1 plus 3t is 5q. It's a multiple of 5, therefore 1 plus 3t is congruent to 0 modulo 5. This kind of technique always works. So if you have multiple of something here and then also in the modulus, you can simplify. And then you get the t value, great. But wait a minute, what are we looking for? Are we looking for t value? No, we are looking for x value, right? X value. X value is 1 plus 5t, and t is 3. So we get 16, and that checks out with the previous answer. Now look at the second solution here. Maybe I should have named it as third solution, I don't know. Whatever. This solution here doesn't really look efficient. Well, it looks at first glance this is easier, but if you sit down and try to do this paper and pencil computation for all these 5 numbers, maybe your mind will change. And imagine 200, 300 years ago, how would people have thought? And also, what if you have much bigger number, not 5 and 25, but much bigger prime number, say for example 101 and 101 squared, for example, then this kind of reduction will make a lot more sense. And nowadays computers can handle all those kind of things, right? Yes or no? For small prime numbers, yes. But for prime numbers of 25 digits, oh, good luck. So the same kind of reduction technique that mathematicians 200-300 years ago worked out, or even earlier as a matter of fact, those kind of things works out for relatively small numbers are working exactly the same way for computers nowadays, except that we are doing that for much bigger numbers. So the mathematical idea behind all those, that's still valid. Remember these kind of tricks. See, binomial theorem, yeah, but don't panic. You don't really have to do them all. Just the constant and the linear term matters. And then the rest is easy computation and appropriate reduction. Now, can you do the same thing to mod 200? Yeah, you can, but we need a little bit more. Mod 200. 200 is a composite number with multiple prime factors. It can be factored like this. 5 squared times 2 to the third power. So this problem can be separated into these two smaller problems. F of x is congruent to 0, mod 25, and f of x is congruent to 0, mod 8. Thanks to the Chinese remainder theorem. Remember? Chinese remainder theorem goes like this. We have to have pairwise relatively prime moduli. Yes, we have 25 and 8. They are relatively prime. And then a part is all 0. Capital M is the product of them all. So we're in precisely the same setting as the Chinese remainder theorem. So we reduce one complicated problem into two easier problems. What if we have, say, 7 prime factors here, or 10 prime factors here? The same. Using the Chinese remainder theorem, you can decompose this one complicated congruence into 7 simpler congruences or 10 simpler congruences, depending upon how many prime factors there are. In this particular problem, we already did modulo 25, and then we can work out modulo 8 similarly. And then we get this conclusion. X is 16 mod 25, and x is 4 mod 8. That leaves us in 116 mod 200. It's going to require a bit of a dirty computation, I think. Let's see. What are the numbers? What are the whole numbers of mod 16? I mean, congruent to 16 mod 25 up to 200. Well, 25 times 8 is 200. So there are 8 such candidates. Among those 8, you can select the one that is congruent to 4 mod 8. It's not going to be too bad. You're going to end up with 116. The detail is left to the students. And then the verification by Mathematica, I just wanted to make a point. There are that many to consider. Alright, so much for the motivating example. We're going to resume the real thing in the next video.